Hi, everyone, and welcome to another episode of Conversations with an Astrophysicist. So we're here at Know the Cosmos. I am your host, Scott Lewis, and with me, as always, our astrophysicist, Dr. Katie Mack, coming to us from the future in Melbourne, Australia. How are you doing, Katie?
I'm all right. It's a beautiful Saturday afternoon.
That's good. Is it warm down there?
No, it's
No.
it's all autumnal now, and the summer is kind of over.
Wah, wah.
So,
It
yeah,
was 33 Celsius today in Pasadena. It was
that's pretty warm.
pleasant. I was
Yeah.
enjoying it. I was enjoying it quite a bit. So for those of you that have never watched this before, welcome. Actually, I should probably tweet out that we're live. That might help. And then, oh yay! I'm always producing and doing all the things. So there you go. That's out on Twitter now. But so for those that have never seen this before, I'm driving the internet and hosting at the same time and doing all the crazy things. But what we do here over at Conversations with Astrophysicists is we have, surprisingly enough, a conversation with an astrophysicist about something awesome. And this is our second episode on gravitational lensing. So we started off last week, not last week, but I think 3 weeks ago was our
Yeah.
last episode. Yeah, I think it was 3 weeks because we delayed a week, or I did because I had stuff and things. But we started off on gravitational lensing. What is it? Mainly focused on strong gravitational lensing. That went along with a press release that was coming out at that time by just by happenstance, and then again, completely by accident. This is going on with another press release from the Hubble Space Telescope yesterday in Science magazine about some new information about dark matter, which, for those of you that don't know, I'm a co-host on, and Katie Mack, was with us bringing her amazing expertise to Hubble Outreach. And I think I thanked you on air then, but and off air too, but thank you again for waking up at like 5:30.
Yeah, it was really early in the morning, actually.
And I appreciate it, and the internet appreciated it, and even like what I love most is that David and Richard, the two that were publishing the papers there, really appreciated you coming out, and so we had people from all over the world for the show, and you woke up early to bring your awesome science, which we will, or at least I will, take advantage of today. So if you want to interact with us, the best way is going to be using the Q&A app. So whether you're watching this embedded somewhere with YouTube, you'll see on the lower left-hand side there will be a thing. This is like we're answering questions. Click on that, and you can ask us questions, and we will try to answer them, and it will timestamp when we answer them. Also, I will be monitoring the comments on YouTube, so I see that Inviting Sauce asked if they were early an hour ago, and yes, you were. But now you're on time if you're still watching us, Inviting Sauce. And then the other thing, again, is Twitter, where I am down here at Scientific Scott, and Katie is, as I switch to her camera, she is at Astro Katie. And you can also follow all of Know the Cosmos at Know the Cosmos, one word. So now I think I have all the things out of the way. Let's actually talk some science. So let's do a brief recap. Okay, what is gravitational lensing? What causes it? How do we know it's there? What's going on there with that?
Okay, so we talked about this last time, but
Right.
basically Einstein's idea about what gravity is that gravity is a distortion of kind of the fabric of space-time. And so if you've probably seen the illustration of sort of like a rubber sheet, and there's a ball in the middle and it causes a dent, and that's kind of a picture of how gravity works in this general relativity picture. And you have to kind of generalize that to another dimension because, of course, our space is three-dimensional. But basically, the idea is that whenever there's something massive, it bends space-time. And
Right.
When light is traveling through space-time, tries to travel in a straight line, but if space-time is bent, it curves around, following the curvature of space-time. And so if you have a mass somewhere in space, then light that's passing by it will get diverted a little bit, and that's called gravitational lensing.
Mm-hmm.
And the reason it's called lensing is that it's very similar to if you have like a glass lens and you send light through that glass lens, it alters the direction of the beams of light.
Right.
And gravitational lensing does a similar kind of thing.
And that's one of my favorite things to do when we're talking about that is it very carefully breaking up the stem of a wine glass and sanding it down so it's nice and smooth, and then having an image behind there, and you can actually watch that go on, and showing that that perfect like Einstein ring effect is what it's trying to show.
Yeah, and we talked about that a little bit last time. Where with strong gravitational lensing, that's when you have the space is distorted so much that that if you have a massive object and something's behind that object, then the light travels past and shows you like multiple images of the same background source because you're getting light coming from two different directions toward you, or several different directions. You can have many images of the background source, and that's called strong gravitational lensing. That's where you have multiple images, and it has this really major distortion effect, multiplying kind of effect on the image, the thing that you're looking at. And we showed some cool pictures of that last time, so watch the previous one if you're interested in that.
And subscribe while you're at it for more.
So I mean, do you have one of those pictures handy just to give an idea of what that strong lensing looks like?
Yeah, so
I could show one.
So I mean, let's see here, the horseshoe Einstein ring. So let me pull this up. Okay. Since I didn't have it ready, but we just roll with it. It's cool. So right there.
Yeah. So this is a great picture because this shows the sort of orangish thing in the foreground is a large, massive galaxy, and that's acting as a lens for a little blue galaxy behind it, somewhere very distant, and that little blue galaxy is being stretched out into these sort of arcs, this kind of ring shape, and that's because it's being distorted as it's coming around the foreground galaxy, and that's strong gravitational lensing. It has a really big effect.
So so now that we've seen strong lensing, what's weak lensing, and how is it different? Is there something else going on with the foreground objects that makes it weak, or is it just that it didn't eat its Wheaties that day and or what in that cosmic day, I suppose?
So weak lensing is different in the sense that, well, sort of two ways. One is that you usually don't see multiple images with weak lensing. You see there's a little bit of a distortion to the image. Sometimes it just kind of squeezes it a little bit in one direction, and it's usually it's farther out from the really massive object, or it's just in a sort of it's being distorted just a little bit by a smaller mass thing, or less sort of less mass between you and the distant object. And usually you can't really see it easily with just one background image. Usually it's when you see a whole lot of images all distorted in a similar way. And I have a little illustration of that I will share with screen share. Hold on a sec.
Screen share.
So this is an illustration of
I love this image.
Of strong and weak gravitational lensing. So this is a simulation. This is just a thing to illustrate. And what you can see is on one side you see this sort of this really strong distortion where you get these kind of arc patterns and this sort of circular distortion. So that's where the really big mass is, and that's distorting all the background things.
Right.
But then if you go far away from that, up into the corner, that's far from where most of the matter is, where most of the distortion is. Mm-hmm. And these objects back here, these are far distant background objects, and so you imagine they might be all elliptical galaxies, but they have kind of random orientations. But when you look at the zoom in picture on the right, you can see that on average they're a little bit more likely to be distorted, to be sort of lying sort of perpendicular to the direction toward the source, so like along a tangential kind of arc direction. So they're mostly aligned in a sort of upper left to lower right direction. And for each individual galaxy, it might just be that that galaxy happened to be an elliptical galaxy that was oriented in that way. But when you take the whole lot of them, you see that more than you expect are aligned in that direction, and that tells you that probably on average there's a big mass off to the lower left. And so that kind of thing is weak lensing, where basically you have so little distortion that you have to look for it statistically. You have to look at a large number of background objects, and they're only just a little bit distorted, and you count them all up and you look at all their orientations and you say that on average probably that means that there's something over there. And you can use that to map out where matter is that you can't see. So it's really great for mapping dark matter, because dark matter is some kind of matter that we can't see. It doesn't emit light, it doesn't absorb light, all of that.
Right.
But it has mass, and so it distorts space. It causes these dents in space, and so it creates these lensing effects. And you can use weak lensing to see where dark matter is, even if you can't see the regular matter. And so there have been some fantastic examples of being able to map out the dark matter by using weak lensing, by looking at all of these distant background galaxies and figuring out what their sort of average orientation is.
Right. Now, so yesterday we were talking about this a little bit, but we're like sometime that the dark matter is kind of it's more like enveloping the gas. From when we were talking about yesterday in the Hubble Hangouts, where we're seeing that it's more surrounding what's going on. So maybe if we're not seeing if it's not emitting light in the wavelength that our detector is observing, so we're seeing distortion, but we're not necessarily seeing what's going on there. Is that what you're talking about as far as that's what's going on? I guess I'm a little confused on that part. I mean, we're seeing big obvious things with the strong lensing. But when we're talking about this weak lensing, it's just that the object's not bright enough. We're not looking at in the right wavelengths, or what?
No. The issue is that with the weak lensing, the lensing is a lot less powerful. So you see all the background objects, and they're distorted, but they're only distorted a little bit each. And so you don't get that. You don't get those really. You don't get obviously distorted things. You just get a whole bunch of things that are sort of elliptical, but they're sort of all tilted on average in the same direction.
So kind of like an old pane of glass, like here. I mean, so as we have some things are looking fine, but then as we know on some old panes of glass, like right here, something's going on. Right?
Yeah, so an old wavy pane of glass is a good illustration for this, because with weak lensing you don't see something that's so clearly obviously impossible, like these sort of ring galaxies.
Right. I mean, it's not like that wrought iron fence went all Escher on us and just and I'm going to sprout up and it'd be just all over the place. Something's going on.
Yeah, so for this picture, it could be that somebody has you look out the window, you see that. It could be that the fence just happens to have bent spikes on it. I mean, that could happen. Sometimes fences are built that way. But when you look at it, you can kind of infer that even though you can't see the glass, you see the distortion that the glass is doing, and so you know that the glass is there. And you can infer even from that still photograph, probably what's happening there is not that the fence is weird, but that the glass is wavy. And that's the same kind of thing with weak lensing, is that you can infer that space is wavy rather than saying that all those galaxies just happen to be aligned in a particular way.
Right. Okay. So it's not normally when I'm thinking large amounts of dark matter, it's because I'm so focused on frontier fields right now with the Hubble Space Telescope. I'm always thinking really, really big galaxy clusters and large amounts where it's really, really obvious. And we're talking about things that
Right.
it's not quite so obvious, and it's just more dispersed. And so, like,
Yeah.
is there a story at all about how weak lensing was first observed, or is there anything like that? Was there a reason that we were able, because you think if you're not really looking for it, it was just like someone's like, that's kind of weird. Why is that going on?
Mhm.
We've seen this big lensing, but
Yeah.
what's with this
I
tiny
mean,
stuff?
I mean, it's kind of a continuum. As if you have an object that's doing a lot of strong lensing, then as you go farther away from that object, the lensing is weaker and weaker.
Okay.
And so at some point, you can kind of see that there's an average tilting all in one direction, but some of the galaxies are still going to be perpendicular or parallel or whatever. So it's just a matter of looking at lots and lots of background galaxies and seeing that that there are these sort of patterns, and from that you can get some amazing maps of where the dark matter is.
Yeah.
Yeah.
The weak lensing box that you sent me that we were going.
Yeah.
Because that thing is freaking awesome. I'm going to tweet this out here in a second.
Okay.
So this right here is so cool. I love this.
Yeah. So this is trying to map out like a large amount of matter between you and the background source. So this is showing how there's if you're looking at the very, very distant galaxies, which are I guess the things kind of on the far left in this picture, and the light from those galaxies is traveling through a clumpy, complicated universe, and so it's getting distorted a little bit every step of the way, and by the time it gets to you, it's a slightly different shape, and that's sort of a way you can map out large amounts of matter over kind of large distances. There's a picture I think you have, Scott, that shows an illustration of where the dark matter is from one of these kinds of weak lensing experiments, these observations where you can see kind of these clumpy blobs that are the positions of dark matter, or just the total matter. I mean, it's not necessarily dark, but it's the position of matter in the universe based on weak lensing images.
Yeah, let me pull this up here. This the lens dots?
No, there's the blobby
no, I know what you're talking about.
dark matter map.
Yeah, this enormously beautiful that I'm just flaking out on. Let's see here. So this is our universe. So when most of us, and I know when you first sent this to me a few weeks back, the first thing I think about is like the Planck or survey or something like that, where we're looking at the complete sky, which we are, but we're not looking at it for like the cosmic microwave background. What we're looking at here, these gray spots, are clumps of dark matter?
So this actually isn't the picture I was talking about. This is fine too.
Well, then we're going to go here, and then we're going to go to your planet later because.
All right. Yeah, no, this is very cool. So this is a map of all the matter in the universe, basically. So this is based on looking at.
It's on my hard drive, everybody. It's on my hard drive.
This is looking at the cosmic microwave background, where the cosmic microwave background is the light left over from the Big Bang. Right. And if we look at the shape of the spots on the cosmic microwave background, which is a kind of a different picture, we can use that to determine how much the matter has been, how much that light has been distorted as it's gone through all of the matter in the universe between here and there. And we can make a map of where that matter is, and this is a map of where all of that matter is. It's a very noisy map, so some of those bright spots are real, clumps of matter, and some of them are kind of just the noise on the picture. But right. This map is basically, this is a projection of the whole sky, and the bright parts, I think, are where there's more matter, and the dark parts are where there's less matter, and that's based on this going through the entire universe, looking for the looking at the distortion of the light as it's passing through the matter throughout the whole universe. So it's a very cool image.
It is such a cool image. I think it's going to become my desktop background. And I apologize for not,
That's okay.
knowing. I was trying to tweet at the same time,
You're
which
tweeting
you
while
should.
we're doing our hangout.
I'm
How would you do
tweeting
that?
science. I'm tweeting about that. I love that image, the
Yeah.
box. So
Yeah, I
much. I
know. The
had to
box is
share it
pretty
out.
cool.
So
Yeah.
you're welcome,
So you.
internet, and then I'm sorry, Katie, for
That's all
not
right.
knowing which image you were talking about.
That's all
Um,
right. There was an image you showed me that had that you have that's sort of a telescope looking at different redshifts and different and the matter at different
yes.
places and has the
Let's
like
see if I
blobby.
still have that because I might have accidentally closed that window. I might have to get it back. No, nope, there it is. I found it.
Okay.
So let me get that back. Here we go. Yes, because this is a Hubble image. And of course I have all the Hubble images in the world. Let's see here. All right, there we go. So
Yeah, yeah. So
let
this
me
is
zoom
a
in here a
yeah.
little
So this
bit
is
more.
another great illustration of the kinds of maps you can make of where the dark matter is based on weak lensing. And these are weak lensing maps where they look at different slices in time of the universe just by looking at different distances. So if you look at as you're looking farther away, you're looking to longer in the past. And so they're looking at these different slices of the universe, and they're making this great map of where all the dark matter was in that sort of region that they were examining. And so you can see at the bottom of that picture is this sort of 3D rendering
Yes.
of where all the dark matter is, and you can't see that matter, but you can see where it has to be based on the distortion of the galaxies behind it. And so this is like a more local version of that huge all-sky dark matter map, and it's
Right.
basically just adding up that all-sky dark matter map is sort of like adding up all of these nearby ones, except it's done in a slightly different way. But as if you look in one direction and you see, and there's a lot of distortion in one direction and a little bit less distortion in the other direction, then you know that there's more matter in the direction where there's more distortion and less matter where there's less distortion. So you can use that to really map out where matter is in the universe. And
So
that's really handy for looking at dark matter because we can't see dark
yeah, you
matter, but
can't
we
see
can
it. Right.
see through weak lensing.
So with that, so are they just looking at different? I'm going to get technical here, and I hope I'm not wrong with it, but different z values. So they're looking at different redshifting of what's going
Uh,
on to look further back, or how are they able
yeah,
to get
well,
those slices?
yeah. So what they do is they look at different galaxies. Let's say they have a sort of field of view, and there are lots and lots of galaxies in that field of view. Some of them are going to be nearby galaxies, and some of them are going to be more distant ones. And
Right.
they can tell how far away they are by the redshift, which is a measure of how quickly they're moving away with the expansion of the universe. And so they can take all of the nearby galaxies and make a weak lensing map with those, and then the sort of middle distance galaxies and make a weak lensing map with that, and then farther out. And so that's how they can get the different slices of distance in the universe.
So was I kind of right then? The z
Yeah,
values? Yeah. So
sure. Yeah,
okay, so
redshift. See.
two astrophysicists in 2 days have said I'm not completely daft on air. I'm just saying I've got a good track record going for me.
Good,
Um,
good.
and let's see here. I'm going to quickly before because there's a couple more images I do want to talk about, and we did start a bit late,
Okay.
so I know
Yeah.
we're a bit late. But I was going to get to a question that was asked earlier, and I thought it was a really good question. And it was from this on Twitter, if I can find it. This is from Natalie Bueno on Twitter, and she is asking, like, she just watched the first episode. Thank you, Natalie. You are awesome. Do the multiple views make for different sides of the lens object? Okay, do they show the different sides? So I guess more of what she's asking there is like when we're seeing multiple images. So I guess this is more on the strong
That's
lens.
strong.
Are we seeing different sides of it? And that answer is
Yeah, potentially. I mean, generally they're so far away that you don't see much else. Like, so if the object is really distant, it's putting out light rays in all directions, and some of the light rays that are going in different directions when they're leaving the object converge to being the same come to the same point, and so you
Right.
see them in different directions, and in a sense, those are showing slightly different sides, slightly different parts of the background thing. But usually, the thing is so far away that you can't really see around so much.
Right.
Like the
So it's like that
sun
the
isn't
angular
distorted
size
so much
is
that
just.
yeah,
It
I mean
just
it's very yeah. So and the distortion is distorting light rays that are really close to parallel, and so it's not a huge angular distortion. And sometimes in the pictures it looks like there are things that are going kind of opposite directions and then they come back. It's not generally quite that strong an effect,
right.
but you get things that were going in different directions. And one of the things that can happen is that you're going through different parts of space-time, or you're taking different paths, and so that can, as we talked about last time, you can get time delays, and that's really cool.
Right. And here's another one too that I hit on. That. This one's from YouTube, so I'm going to click on this one. This is from Inviting Sauce. So thank you for staying with us, even though you came early. It says, can a black hole gravitational lens something? So could a black hole cause a gravitational lens?
Yeah. So certainly, if light is coming close to a black hole, it can be lensed, and by the mass of the black hole, the light can be lensed around it. And actually, if you have seen the movie Interstellar, the picture of the black hole in that movie depends strongly on gravitational lensing being a thing. So if you look up, why that black hole looks the way it does in Interstellar, that's because it's lensing the light behind it, and it makes it kind of this weird shape with like a halo and a disk in front, and that's kind of where that comes from.
I know you're not one to toot your own horn, but I am one to toot your horn. Haven't you you've written something about the science of Interstellar, right?
Yeah, I wrote a thing for BuzzFeed about Interstellar. So
you should totally tweet that out. If not, I will soon, because
okay.
it's so cool. Actually, I was going to attend it, but here at JPL, they had an Interstellar panel talk a couple days ago, and I was going to go, but decided not to because it's a lot of people, and a lot of people did show up. But it was really fun, because getting into the science of it, which I think is awesome.
Yeah.
So I want to show something here too, because we were mentioning about that dark matter map, and it's something that I showed yesterday in the Hubble Hangout, but and I think it does a great job of illustrating what you're talking about with that dark matter map. So let me of what the light's doing between here and there. So let's go here. I hope this is still on me. Yep, it should be. So light starting back here at the source, and there is that dark matter map you're showing, right?
Yeah. So this is an illustration of how the light is being bent around the matter, and so it gets distorted as it's going past the matter, and ends up a sort of different shape when it gets to you at the other end.
Right.
And so we've been able to use these effects to see to like map out where dark matter is in like clusters of galaxies, for instance. So I sent you, Scott, a picture of the Abell 1689 cluster.
You did.
And then there's a map of the dark matter in that cluster.
So here is Abell 1689 from Hubble Space Telescope. Here we are. Beautiful, beautiful, beautiful.
Yeah. So this is a beautiful picture, and you can see the strong lensing as well in this picture, because you can see those arcs around the center of the galaxy cluster. This is a cluster of many, many galaxies. But you can also look at the little tiny dots sort of in the back of that picture, and use that to map out the weak lensing. And look at the distortion of the very distant objects, and then get a map of all of the dark matter in that cluster.
Mm-hmm.
So, Scott, there's another image called high-res DM map, I think, that shows that dark matter map.
Yeah, it's right here.
Yeah. So
There you go.
this is another, this is a picture where they've sort of painted on where the dark matter is based on examining that optical image, and you can see how it's sort of clumpy toward the center, and there's a lot of dark matter in that cluster, and you can see how they've detected some a little bit farther out as well, and that's a way that we can sort of figure out where the dark matter is in individual like large objects using weak lensing, which is very cool. And we've used that to figure out where the matter is in galaxy clusters in order to show that dark matter is there, in order to find out how much dark matter is there. And in some cases, when two clusters collide, the regular matter and the dark matter get separated because the regular matter gets stuck in the middle and the dark matter passes through. And you can use weak lensing to show that the dark matter has passed through in that collision and ended up on the other side. And that's one of the ways that we've been able to both show that dark matter is really a thing that's different from regular matter, and also to measure its properties, like we talked about on the Hubble Hangout yesterday, where we talked about the fact that it looks like when two galaxy clusters collide, the dark matter passes right through, doesn't collide with itself, doesn't feel that interaction, and you use weak lensing to see how the dark matter ends up on either side of this galaxy cluster collision and doesn't interact. And there was a new project that looked at lots and lots of different galaxy clusters and showed that on average the dark matter really doesn't feel anything; it just goes right through.
So using that, you just read my mind. My next question, as we're ending it here, was like, does studying this weak lensing, does studying this really, what does it help us? And you're saying we're learning about one of the biggest questions right now is what's the majority of the mass of the universe?
Yeah.
What's the properties of it? Because we don't know, and we're finding it like yesterday was huge news, and it just. It was completely serendipitous that our show was on this week, but we're finding out new things about dark matter, and which is awesome. And I think it's awesome because I just think it's awesome in general. You think it's awesome because that's what you research.
So I research properties of dark matter. I'm trying to figure out what dark matter is by seeing how it affects other objects in the universe, and weak lensing and also strong lensing are ways we can study dark matter, because although dark matter does have mass, and so it affects how light is moving around in the universe, it doesn't interact through, like, it doesn't emit its own light, it doesn't seem to collide with other things very much. So using the distortion of space-time by dark matter is one of the few ways we can really learn about it, and weak lensing is one of the great tools for that.
That's awesome. So I'm going to end our show here with a question from the Q&A app, because Tom and Paul, our buddies, have been going back and forth. But Ronald asked a question, and so I am going to select that and put it up there. So it will show up on YouTube here in a bit. This is there similar lensing in our galaxy center? So in our galactic core, is there any? Are we able to observe that? Because I know there's so much that we see. It's so bright. Are we actually able to detect any lensing effects from the supermassive black hole in the center of our galaxy?
So I haven't heard of any. I think that it is, as you say, the center of the galaxy is very, very complicated. There's a lot of gas and dust and stars, and there's like outflows from the area around the black hole. There's a lot going on. So I think that I haven't heard of any specific observations of lensing having to do with that supermassive black hole in the galactic center. But maybe if we have better observations, maybe if we're able to account for all these other things going on, we might be able to see that at some point.
And for if any of you out there want to know more about black holes or Sagittarius A star, which is our supermassive black hole, you can check our YouTube channel, because we've done a show about that, and we talk more about it and get into details about black holes, and they're really, really cool. I do want to thank everyone for watching, and the questions from all over on Google+, on YouTube, on Twitter. You guys are all awesome. Thank you for the subscribers and those that have been sharing it out there. Of course, Katie, I want to thank you for being here all the time, and like you really are. Okay, you're one of my own personal astrophysicists, but you're my favorite, and
Okay.
and I'm trying not to offend my other astrophysicist friends, but which is weird to have to say, but you are my favorite, and so thank you for coming back and bringing some amazing science and insight to us all. Follow her, everyone, on Twitter at AstroKatie. I mean, it's not like she has enough followers, but she could always use more. I mean, she's not highly followed. She's just the most followed astronomer in Australia on an entire continent. That's pretty awesome. If you had a collar, I would say flip your collar up, but you don't have one. So, again, thank you all for watching. If you want more like this, please subscribe. Give us we're always looking for some new topics that you'd like us to discuss. We will be back for again, most likely in 2 weeks' time, to do more of a wrap up on gravitational lensing. And then just to go over the strong of the week and everything else, and wrap it all up there.
Microlensing.
Microlensing.
Yeah.
So if you guys have any questions on microlensing, if you have any topics that you'd like us to talk about as well, let us know in the comments here on YouTube. Tweet at us over on Twitter. We're both on Facebook, though we prefer Twitter. Like, we really, really do. Just tweet at us. Or Google Plus. I am pretty active on Google Plus too. So again, thank you all, and we will see you in about 2 weeks.
Bye.
Bye.